Section: Introduction. In this section, we introduce the significance of image editing using natural language instructions, which has become a key area in vision language research. This approach allows users to interact intuitively but also presents challenges, such as understanding complex meanings, accurately identifying areas to edit, and maintaining image quality. Although diffusion models have greatly enhanced image generation, current designs that combine text encoders like CLIP and T5 with diffusion transformers often struggle to follow subtle editing instructions, leading to misalignment between the input image and the desired edits. Recent developments in proprietary multimodal models, such as GPT-4o and Gemini2 Flash, have advanced instruction-based image editing, utilizing extensive vision language capabilities for high-quality edits. However, their closed nature limits transparency and reproducibility. On the other hand, open-source initiatives like OmniGen and ACE++ aim to achieve similar results but still lack in generalization, accuracy, and image quality. Our goal is to bridge the performance gap between open-source and closed-source editing systems while enhancing practical evaluation methods. We believe that existing open-source editing datasets, like AnyEdit and OmniEdit, do not provide sufficient quality and diversity to compete with closed-source algorithms. Therefore, we focus on creating a large-scale, high-quality dataset for training. We categorize editing tasks into 11 major types based on common instructions and develop a scalable data pipeline to generate over 1 million high-quality image instruction pairs. This dataset covers a wide range of editing operations, ensuring it reflects real-world scenarios. Building on this dataset, we propose Step1X-Edit, a unified image editing model that merges the semantic reasoning of multimedia large language models, such as QuenVL, with a diffusion architecture. The model processes the reference image and editing prompts to create a target image latent condition, which is then used to generate the final output image. Our approach effectively balances image reconstruction and adherence to editing prompts. For training, we start with a text-to-image model to ensure aesthetic quality and visual consistency, which can be replaced by existing models like SD3 and Flux. To evaluate editing models, we introduce GEdit-Bench, a new benchmark that captures real-world editing needs and diverse prompts. Our experiments show that Step1X-Edit significantly outperforms existing open-source models and approaches the performance of leading proprietary models like GPT-4o. In summary, our contributions include open sourcing the Step1X-Edit model to help close the performance gap between editing systems, creating a data generation pipeline for high-quality image editing data, and developing GEdit-Bench for more authentic evaluations of image editing models. Next, we discuss related work in controllable image generation and editing. Autoregressive models have been explored for this purpose, modeling images as sequences of discrete tokens and incorporating various forms of guidance for more structured control. However, these models often struggle with high-resolution results in complex scenes. In contrast, diffusion models have emerged as the leading method for high-fidelity image synthesis, excelling in photorealism and diversity. While diffusion models have their strengths, they often rely on static prompts and lack flexibility for open-ended editing. This has led to interest in unified frameworks that combine the strengths of both autoregressive and diffusion models, aiming for more versatile and user-controllable editing capabilities. We will delve deeper into this topic in the next section. Section Summary. In this section, we highlight the growing importance of image editing with natural language instructions in vision language research, noting the challenges of semantic understanding and image fidelity. We propose our Step1X-Edit model, which leverages a large-scale, high-quality dataset and a novel benchmark, GEdit-Bench, to bridge the performance gap between open-source and proprietary editing systems, ultimately enhancing user-grounded evaluation in image editing. Section: Unified Instruction-Based Image Editing Models. In this section, we discuss unified image editing models that combine understanding semantic instructions with precise visual manipulation in one framework. Early models often used modular designs, where large language models generated text prompts or spatial instructions to guide diffusion models, as seen in approaches like prompt-to-prompt and Instruct-Edit. Instruct-Pix-2-Pix trains a conditional diffusion model with synthetic instruction image pairs, while Magic Brush enhances usability with high-quality human annotations. To address data scarcity, GEdit refines text-to-image models into consistent editing models through causal diffusion and self-alignment. Recent models like Smart-Edit and X2i improve the interaction between language and vision by using multimodal attention and reasoning. AnyEdit introduces task-aware routing and visual prompt projection, while OmniGen uses a single transformer to encode text and images together, reducing reliance on external encoders. Models like Gemini and GPT-4o show strong visual fluency through joint training, indicating a shift towards tightly integrated, instruction-driven editing frameworks. However, many existing methods are still task-specific and lack general-purpose editability, often not supporting incremental editing or fine-grained region correspondence. These limitations inspire our development of Step1X-Edit, which integrates multimodal reasoning with controllable synthesis for scalable and interactive image editing. Regarding our data pipeline, we recognize that current image editing datasets are limited in scale and quality. To fill this gap, we aim to create a large-scale, high-quality dataset for image editing tasks. We start by web crawling diverse image editing examples and categorize them into 11 distinct categories to cover most practical editing needs. We designed a sophisticated data pipeline to collect over 20 million instruction image triplets, filtering them down to over 1 million high-quality pairs through rigorous checks by multimodal large language models and human annotators. Our Step1X-Edit dataset stands out in scale compared to existing datasets. For specific tasks, we follow a detailed process. For subject addition and removal, we annotate our dataset using Florence 2 for various semantic details and apply SAM2 for segmentation. Editing instructions are generated with the Step-10 model and reviewed manually. For subject replacement and background changes, we use similar preprocessing steps and employ Qwen 2.5-VL for identifying target objects, followed by content-aware inpainting. In color alteration and material modification, we estimate depth with ZeoDepth and use ControlNet to generate new images while preserving object identity. For text modifications, we distinguish valid edits using PPOCR and the Step-10 model, finalizing outputs through human post-processing. In motion change tasks, we extract frame pairs from videos and use BiRefNet for separation and flow estimation, annotating motion changes with GPT-4o. For portrait editing, we collect beautification pairs and validate them manually. In style transfer, we generate photorealistic images from stylized inputs or vice versa, depending on the target style. Lastly, tone transformation focuses on global adjustments using algorithmic tools to simulate realistic changes. Section Summary. In this section, we discuss unified instruction-based image editing models that integrate semantic understanding with visual manipulation, highlighting advancements like Step1X-Edit, which combines multimodal reasoning with controllable synthesis for scalable editing. We also outline our efforts to create a large-scale, high-quality dataset for image editing tasks, detailing the systematic collection and categorization of over 20 million instruction image triplets, ultimately retaining more than 1 million high-quality examples. Section: Our Method. In this section, we describe our method, which consists of three main components: a multimedia large language model, MLLM, a connector module, and a diffusion and transformer, DIT. We begin by inputting the editing instruction and a reference image into the MLLM, specifically using Qwen VL, along with a system prefix. This allows the model to understand the relationship between the instruction and the visual content. To focus on the relevant semantic elements for the editing task, we remove the token embeddings linked to the prefix, keeping only those that match the editing instruction. Next, we pass the extracted embeddings to a lightweight connector module, like the token refiner, which compresses them into a more compact textual feature representation. This refined feature replaces the initial text embedding generated by the T5 encoder in the DIT network, such as Flux. We also calculate the average of all output embeddings from Qwen, which we then project through a linear layer to create a global visual guidance vector. This enables the image editing network to utilize Qwen's enhanced understanding for more precise editing. To train the token refiner effectively and support rich cross-modal conditioning, we adopt a token concatenation approach inspired by FluxFill. This involves feeding both a target image and a reference image into the system. The target image is encoded with added Gaussian noise to enhance generalization, while the reference image is encoded without noise. We concatenate the resulting image tokens, creating a fused feature that doubles the token length for the final visual input. We train the connector and the DIT together, initializing both with pre-trained weights from our Qwen and DIT models to improve convergence and performance. We set the learning rate to a small value to ensure stability and speed in training. By integrating structured language guidance, token-level visual conditioning, and strong pre-trained models, our method significantly enhances the system's ability to perform high-quality, semantically aligned image edits based on diverse user instructions. To evaluate our image editing models, we have created a new benchmark called GEdit-Bench. This benchmark aims to gather real-world user editing examples to assess how well existing algorithms meet practical editing needs. We collected over 1,000 user editing instances from platforms like Reddit and categorized them into 11 distinct groups, ensuring diversity by filtering out similar instructions. Ultimately, we compiled 606 testing examples with reference images from real-world scenarios, making the benchmark highly relevant for practical applications. To protect privacy, we implemented a thorough de-identification process for all user-uploaded images before using them in our benchmark. For each original image, we conducted a reverse image search across various public search engines to find visually similar and semantically consistent alternatives. If we couldn't find suitable public images, we carefully modified the editing instructions to maintain fidelity with the original user intent. This approach ensures the ethical integrity of our benchmark dataset while preserving the essential characteristics needed for accurate evaluation of image editing models. Section Summary. In this section, we describe our image editing method, which integrates a multimedia large language model, MLLM, a connector module, and a diffusion in transformer, DIT, to enhance semantic understanding and accuracy in editing tasks. We also introduce the GEdit-Bench, a benchmark created from over 1,000 real-world user editing instances, to evaluate the performance of various image editing algorithms while ensuring ethical considerations through a de-identification protocol. Section: Evaluation on GEdit-Bench. In this section, we evaluate various image editing algorithms using the GEdit-Bench. We focus on both open-source solutions like InstructPix2Pix, Magic Brush, AnyEdit, and OmniGen, as well as proprietary algorithms such as GPT-4o, and Gemini2 Flash. We utilize three metrics from Vi-score: semantic consistency, SQ, which measures how well the edited images follow the given instructions; perceptual quality, PQ, which assesses the naturalness of the images and any artifacts; and an overall score based on these evaluations. For our automatic evaluation, we use the advanced MLLM model GPT-4o and also include results from the open-source model Qwen 2.5-VL72B for reproducibility. Each image in our benchmark is paired with instructions in both English and Chinese to evaluate model performance across languages. For English instructions, we assess both closed and open-source models, while for Chinese instructions, we only test models that support Chinese prompts. During our evaluation, we noticed that some closed-source systems, like GPT-4o, may decline certain instructions due to safety policies. To address this, we report two scores: the intersection subset, which includes images successfully processed by all models, and the full set, which encompasses all samples from GEdit-Bench. We calculate average scores only for cases where models successfully generate the target image, excluding instances where no result is returned due to safety concerns. Our findings show that Step1X-Edit excels, outperforming open-source models across 11 evaluation criteria and surpassing closed models like Gemini2 Flash and GPT-4o in areas such as style and color changes. Step1X-Edit also maintains strong performance with Chinese instructions, demonstrating its effectiveness without needing masks during editing. To further assess the subjective quality of our image editing results, we conduct a user preference study with 55 participants who evaluate outputs from 4 algorithms: Gemini2 Flash, Dubao, GPT-4o, and our Step1X-Edit. Participants rank the editing results in a blinded setting to reduce bias, using a 5-level quality scale. We convert these qualitative ratings into numerical scores for consistent comparison with VISE scores. The average preference scores across all editing tasks highlight the effectiveness of Step1X-Edit, showing that it achieves quality comparable to other leading methods. Notably, Gemini2 Flash receives high user preference scores due to its strong identity-preserving capabilities, which participants favored in the study.